Good morning, my name is Hugo Legaria and I am dedicated to the design of contact lenses and their fitting. I want to thank Carlos Mayero for his trust and for having invited me to participate again in class, and I feel very honored by this invitation, and this time I am going to share a presentation on corneal topography and its application in the field of contact lenses. And the idea is to focus on how to extract information that is useful to be able to calculate a lens that is based on the topography. And it is not so much the data analysis itself, but how to know what things we have to consider the most important of the topography in order to achieve a good fitting. When we work with topography, we have to know that we have 4 available maps, and these are 2 of curvatures, these being the axial and the tangential. The elevation, that refers to a sphere and tries to mathematically represent the cornea in the best possible way, and on that sphere we obtain information about how many microns we are up or down with respect to the corneal tissue, and the refractive map that gives an optical entity to the cornea and therefore gives us a representation of refractive power in each area, concentrating on fitting, geometry and wear. And the maps that provide the most information are the axial, the tangential and the elevation. The axial map and the tangential or instantaneous differ fundamentally in those with mathematical conditions that are set to the software to generate the representation in the case of the axial map. It puts as a condition that the entire surface that is generated must have a rotation axis in the center of the visual axis. And this is therefore that we are going to see the areas that have more irregularity, that are quite smoothed, especially transplant joints, and corneas with intrastromal rings. All those surfaces that they have some type of undulation, and in the axial map they are smoothed. And it is very useful to see in a global way what the geometry that the cornea has, if it is an ectasia or if it is a regular cornea. But let's say it does not have that detail in the peripheral areas, that if it gives us the instantaneous or the tangential map. And in this case, the condition that the surfaces represent the cornea have its axis of rotation in the center, and it is not there. Therefore, there are multiplicity of curvatures that will complete that shape and will give us a more precision in the peripheral areas. And the small one represents very well how the cornea closes, where the end of the graft is located. And we will see that in detail in the topography with very warm colors, precisely representing a very closed radius of curvature that in an axial topography cannot be seen. On a tangential map, we obtain better observation of irregularities, more precision in the peripheral area, and it is also very useful to determine the size of an ectasia. Many times in the axial map, everything is seen in red. However, when we look at the tangential, we see with greater clarity where the area with the highest point, with greater elevation really is, with respect to the rest of the tissue. Which this does not have much variation with respect to the normal, but it helps us to identify the exact diameter of the area with greater irregularity. The elevation map is, from my point of view, the one that gives us the most important information for calculating lenses. And what it does is, based on the height of the cornea in each area, the software generates a surface that is called a sphere of best fit, or BFS for its acronym in English. And that tries to represent in a sphere the most similar shape that stimulates the cornea, saving the distances that it can have precisely because it is an ectasia.
Un comprobado líder en la práctica de lentes especiales y ojo seco. Cuando la precisión importa.
Such as high eccentricity or asymmetries, the height differences that it has in each area. And the elevation map will produce them in colors, and it works as we are seeing here on a tomography, where the sphere of best fit is below the cornea on the elevation map, and we are going to see the cornea painted in warm colors because it is above the reference sphere, and what happens in the center, in the mid-periphery area, the reference sphere here is above the cornea, and that area we see painted in colors cold because the cornea is below. And when we reach the edge, we see that again the reference sphere is within the corneal tissue. That is, the cornea is higher and it will once again have warm colors on the map. On the map, we will see something like this. In this case, it is a topographer, which shows the colors, and when I move the pointer over each area, it indicates the values in microns. Other topographers directly represent the map in colors and place the numbers above in each area so that you know how many microns there are of difference up or down of the cornea with respect to the reference. On the right side, on the map, here we see the BFS at 3 millimeters, at 5 millimeters, and 7 millimeters. And you can see how it changes the number, in brackets 5.58 for 3 milliliters, 5.79 for 5 milliliters, and 6.25 for 7 milliliters. That is to say that it is obviously a cornea with a fairly large eccentricity, and therefore the reference sphere for 3, 5, and for 7 millimeters, it gradually flattens, and the graph that we are seeing, it changes. And it is stimulated based on the 7 millimeter reference sphere, and it is always convenient to work with the 7 or 8 millimeter reference sphere because let's say that the area on which the lens that we are going to fit will land, it does not make much sense to work on 3 millimeters in diameter because the lens will land much farther on the refractive map. As I mentioned before, what it does is consider curvature under Snell's law, and that the cornea has in each area and assigns it a refractive power to have an idea of what the optical behavior of the cornea will be. The two topographies that we are looking at correspond to the same eye. On the left side we have the axial map, and on the right side we have the refractive map. In the central area, practically they do not differ, and notice that it indicates 43.39D in both cases, because they are well centered. And as we move away from the center, it's where we will find differences between the refractive and the axial. An important point to take into
Punto a tener en cuenta
consideration is that
importante
of the
es que las
scales.
escalas,
Especially if we are monitoring
sobre
patients,
todo si estamos
it is
haciendo un
important
seguimiento de
to always work
pacientes,
with the
es
same scale.
importante trabajar
And
con la misma
if we are seeing
escala siempre.
photographs of
Si
different
estamos
patients
viendo
and we want to
topografías
take
de
our
distintos
comparisons,
pacientes
it is always
y queremos
advisable
hacer
to match the
comparaciones,
scales or work on
conviene
an absolute
siempre usar
scale.
las escalas o
And
trabajar
on
con
the
la escala
absolute
absoluta.
scale,
La escala
each
absoluta
topographer always
es
determines a color for a
cada
certain
topógrafo
curvature.
determina un
So
color siempre
if I
para una
quickly look
determinada
at
curvatura.
a topography on an absolute
Entonces,
scale
si yo
and then I
miro
see
rápidamente una
that there is a red
topografía
color,
en escala
it is
absoluta y
automatically
veo que
a
hay
cornea
colorado,
with
ya
ectasia or
automáticamente
some
sé que se
irregularity.
trata de una
And then
córnea con una
if it is
ectasia o
almost
alguna
green,
irregularidad.
all green, should I say,
Y si
which is
está
a
tapizado
fairly
de
regular
verde, es una
cornea,
córnea
and
prácticamente regular.
normal values, when we work
Cuando
with
trabajamos con
normalized
escala
scales,
normalizada,
the
el software del
topographer
topógrafo
software adjusts the
ajusta
scale
la
for the
escala
eye in
para
this
ese
particular
ojo
case
en ese
to
caso en
obtain a
particular,
greater range of
para obtener
differences
el mayor
and to
rango de
appreciate as
diferencias
much
y
detail
que
as
haya una
possible.
mejor, un mayor detalle de lo que estamos
But
visualizando.
when I go to
Pero cuando
compare
yo
with another
lo vaya a
topography,
comparar con esa otra
possibly the scales are
topografía,
different,
posiblemente
so
las
I
escalas
cannot be
estén
guided by the
distintas.
colors, but
Entonces
I
no me
have to
puedo
see the
guiar por los
numerical
colores,
values.
sino que tengo que ver las
The
variables
adjustable
numéricas.
scale is very useful,
Y la escala
especially
ajustable
when we
es
have
de gran utilidad,
orthokeratology
sobre todo
patients
cuando
and
tenemos
we want
pacientes
to
de
see very
ortokeratología
subtle changes.
y
We
queremos
can
ver
make steps
cambios
of
muy sutiles, podemos hacer
0.50D or
pasos de 0,50
0.25D
a
to see
0,25
those
para
small
ver
variations with
esas
color.
pequeñas variaciones con color. Bien,
Entering what would be
yendo
the
directamente a lo que
application
sería
of
la
topography
aplicación
for lens fitting,
de la
there are
topografía
two
para
ways
la
of
adaptación de
working one,
lentes,
and this is
hay
through lens
dos
fitting
formas de
stimulation
trabajo.
software that
Una
practically
es
all
mediante el
topographers
software
on
de
the market have
simulación de
incorporated.
adaptación de lentes que prácticamente traen incorporados todos los topógrafos en el mercado.
But
Y
that
eso
would mean that
significaría
one
que
works
uno
with the
trabaja con
topographer
el topógrafo,
or
uno
that
tiene
one has
acceso al
access to the
topógrafo
topographer
para
to
acceder a ese
work with the
software.
software.
La
The
otra
other
forma
way
de
of
trabajo
working
es cuando
is
uno
when one
recibe
receives
el
the
reporte
report
de la
of the
topografía que
topography
lo trae el
that the
paciente,
patient brings,
pero tiene
but
impreso,
it
no
is
tiene
printed and
acceso
one
a
does not
trabajar
have
con el
access to
software.
work with the software.
Según cuál sea
Depending
nuestra
on our
situación,
situation,
lo vamos a
we are
manejar
going
de
to
una manera
handle it in a
distinta.
different way.
Voy a
I will
explicar
first
primero
explain how it would be
cómo
the
sería
case
en el caso
when
cuando uno
one
trabaja
works with the
con el
topographic
reporte
report.
topográfico.
In
En
that
ese
case,
caso,
it is
es
important to ask the
importante pedirle
patient
al
that when
paciente
they give the
cuando
topography,
le den la
either
topografía,
on
ya sea en
disc
3D
or
o
printed,
impresa,
that they
que le
give the
den el
elevation
mapa
map
de
to be
elevación
able to obtain the numerical values of
para poder
elevation
sacar los
difference.
valores numéricos de diferencia de elevación.
In these
Realmente,
cases, we have
en
to
estos
first
casos,
determine what
nosotros tenemos
type
que
of lens
determinar
we are going to
primero qué
use
tipo de
and
lente
its
vamos a
diameter.
usar, qué diámetro,
Take into account
y
that
tener
the
en
full
cuenta
diameter
que
of the
el
lens
diámetro
is not
completo
the
de la
one
lente no es
that
el
will
que va a
bring
estar
that
apoyando
will be
sobre la
resting
córnea,
on
sino
the
que
cornea at the
el
edge,
borde,
and we have
digamos,
the
la
area
parte del
of the
bisel que
bevel
queda
that is
levantada
raised further
y un
inside
poquito
the
más
area
adentro
where the
está la zona
optical
donde
area
termina la zona
ends,
óptica
and is the
y está el
pre-bevel
prebisel que
which
sería donde
would
la lente
be where
aterriza.
the lens
Por
lands.
ese
For
motivo
that
es que si
reason,
nosotros,
if
por
is
ejemplo,
that
vamos a
if,
tratar una
for
lente de 9
example, we are going
milímetros,
to fit a 9
lo que vamos
millimeter
a hacer
lens,
cuando midamos
what we
los
are going
valores
to
en la
do when we
topografía
analyze the
es
topography
hacer
is to
medidas
take the
en referencia
measurements
a
in
8
reference at
milímetros,
8
es decir, un
millimeters,
milímetro
that
menos
is
que el
1
diámetro de la
millimeter
lente.
less than the diameter of the
Si
lens.
adaptamos una lente
If
de
we
10
fit a 10
milímetros,
millimeter
lo que
lens,
vamos a hacer
what we
sería
are
la
going to
misma
do is survey the
topografía
topography
para una
of a
zona de
9
9
millimeter
milímetros de
area,
diámetro,
that
es
is
decir, un
1
milímetro
millimeter
menos.
less.
Es una relación
And it is an approximate
aproximada,
relationship,
pero
but
sirve porque
it
lo
is
vamos bastante
useful because
precisión.
we obtain enough precision. And
Basta el
it will be
diámetro
the
sobre el cual
diameter
esa
on which
lente
the
va a estar
lens is going
aterrizando.
to be landing
Y
on,
por eso es que nos
and for this
interesa
reason, we are
justamente
precisely interested
ver
in seeing what the difference in height that the corneal surface has in that diameter that we will be using. Using formulas to calculate sagitta, simulations can be made and to know precisely how many microns the sag of a lens varies. And when I adjust or flatten X amount of diopters, these calculations are summarized here. For an 8.5mm diameter lens, if I adjust or flatten one diopter, it modified its sag by 27 microns. That is, if I flatten, the edge will rise 27 microns, and if I adjust it, it will depress 27 microns. For a 9mm, 32 microns, and for a 9.5, 37, and for a lens of 10mm, 43 microns. This table is very practical because quickly, knowing the number of microns that I can see on the elevation map of the difference between the main axes, I can, by means of a simple calculation, know how much torsity I have to give to the lens, so that it fits well. Here we have an elevation map where it shows us the color and the numerical values. Now, notice that we have two scales, on the left and below, where it indicates in millimeters the distance to the center and the diameter that each zone involves. Analyzing this line of numbers that mark us 43 and 40 near the row of 8, they are close to 8 millimeters in diameter. And they are telling me that for a diameter of 8 millimeters, the cornea is raised 43 microns, compared to the expected reference of the map. And therefore, if I want the lens to support properly, I have to raise the edge 43 microns. And looking for the table that I mentioned before, if I am saying that the lens is going to land at 8 millimeters and this fitting a 9mm lens that supports 1 millimeter less, I know that 32 microns are equal to 1 diopter. Therefore, if I have to raise it to 43 microns with a simple rule of 3, I know how many diopters I have to raise, so that it rises. And this is a way of working directly, doing calculations when you have the topography printed or in digital format. If one has the possibility of working with the software, it is easier because you can do the fluoroscopic simulation and in the simulation directly obtain these calculations or simulate. And in this case, in a cornea with a stigmatism of approximately 2 diopters, this is a simulation of a spherical lens where we clearly see that it is resting on the plane of the axis. I am measuring in the center that we have 27 microns of elevation. The central TLT, the lens supports in here where I am seeing the graph of the profile.
Whether you're helping your patients with the daily irritation of dry eyes or combating other ocular surface diseases, Boston Sight Sclero has the data-backed science and experience to help them see the world through a whole new lens.
And this graph represents the thickness of the tear in each area. And in this case, we are analyzing or on the axis of 22 degrees, which is the one that is observed dotted in the software. And I could position myself on any other axis. And this graph is observed on the right will change depending on the tear profile of the axis analyzed. And in this box that we see here, this is where I go loading the lens parameters to do the simulation. And where
El
it says BC1
BC1
and
y
BC2,
BC2
that is
es
the
la
curvature
curvatura
that I want
que
the
el
lens to
promedio con
have in its
con la
base
curva
curve,
base,
while the
y
PC1,
BC1,
PC2, and
BC2,
PC3
BC3
are
y
the
etcétera
peripheral
son las
curves
curvas
that are loaded the
periféricas.
radius
El
of
total de los
curvature that
cuatro
I want the
curvos
lens to
obtenemos
have
el
in the
total en D,
peripheral
pero son las
areas.
periféricas.
And where
Por
we
ejemplo,
observe
acá W
WPC1 and
WPC1,
WPC2,
WPC2
etc.,
hace
it
mención
mentions
al
the
ancho que
width
quiero
that I
obtener
want to assign
cada
to
una de
each
esas
of
bandas
these peripheral
periféricas.
bands. And I am
Esto lo
loading the
deja dando
millimeters
los
of
milímetros de
curvature
curvatura
and the
y el
width in
ancho en
millimeters.
milímetros.
In
Esto
this
es
image,
para
we
mostrar
can
cómo
see the
se
tear
ve el
profile
perfil de
analyzed
lágrima
in the most curved
analizado
axis.
en el eje curvo, la
And
misma
with the
lente
same lens
lápiz,
as
mismos
before,
parámetros
the
de
same
adaptación.
adaptation parameters,
La lente
people
está
are
apoyada en el eje de 20
leaning
grados
on
y
the
el
20
contra
degrees
eje
axis,
queda
while the counter
completamente
axis
levantada.
remains
A la
completely
altura donde
raised.
tendría que estar
At the height where
aterrizando,
it should be landing,
tiene
it has
una
a height
diferencia de
difference
altura de
of
45
45
micras.
microns.
Es decir, como
That
mencionaba
is,
antes,
as I mentioned
buscando la
before, looking at the
tablita,
table, if in the 8mm zone it had
si en la zona de
45
8
microns
milímetros
and I want to lower it
tenía
to
45 micras y
approximately,
yo
let's
quiero
say,
bajarla a una
30
zona de
microns
30,
for a
para una
9mm
lente de 9
lens,
milímetros,
it will be
con
enough to
ajustar
adjust
una
one
dioptría,
diopter
ya la
and the
lente
lens
va
will
a
close
cerrar 32
32
micras.
microns.
Entonces
So
yo
I
sé
know that
que
in this case, I
directamente
could
en este
adjust the
caso
counter axis with
podría
respect to the
ajustar
flat
el
axis by
contraeje una
1
dioptría
diopter,
y ahí
and
prácticamente la lente va
practically
a
the
quedar
lens will remain
apoyando parejo
resting
en los
fairly
dos ejes
evenly on the
principales.
two main axes.
En este caso es
In
una
this case, it is
simulación
a simulation
directamente ya
directly,
una lente
and to a lens
con
with toric
curvas
curves,
teóricas.
note that
Fíjense
BC1
que BC1
indicates
dice 5,71 y
7.71
BC2
millimeters and
dice
BC2
8,08. Es decir
8.08.
que
That is to
ya
say
tenemos
that we
representadas las
have
dos curvas
represented
de
the
los
two
dos ejes
curves
principales
of two main
y ya el
axes, and
fluorograma
the
mejoró
fluorogram, it
muchísimo.
improved a lot later.
Después
And
tenemos
we have
PC1 que es el
PC1,
actual
which is the
diseño, y ese es un
pre-bezel, and
diseño bastante
PC2,
simple.
which is the bezel. It's a fairly
Vemos en
simple
23 y en
design, and
113
we see at
Hz
23
cómo los
and
perfiles de lágrima
113
son
degrees that the
bastante
tear profiles are
homogeneos,
quite similar,
tienen un buen
and
aterrizaje y un
they
despegue
present
que
a
se
good
entiende
landing
a
and a central
27
clearance of
micras
about
en
27
promedio.
microns.
¿Sí?
It is a
Es una
simulation
simulación
through
a través
software.
del software. ¿Por qué
And
hablo
why I talk a
bastante
lot
del
about the
tema del
subject of
software?
software.
Este
This
software
function is
está
practically in
prácticamente
all
en todos los
topographers.
topógrafos. De
In
hecho, hay
fact, they
topógrafos
are
que ya vienen
topographers
con diseños
that come with
precargados
preloaded
directamente
designs
de
of
uso
different types of
comercial,
lenses for commercial
para que uno
use,
elija la
so that
marca con
one
la que
can choose the
trabaja, porque
brand
tiene
with
caja
which they
dentro,
work with.
y hasta incluso el software
And the one
genera
that has test boxes and even the
una
software
lente
generates an
ideal
ideal lens
y hace
and
la
makes the
simulación para
simulation
que uno
so
vea
that
cómo
you can
quedaría.
see how it would look.
Si uno le
And if
busca
you like to
diseñar su
design your
propia
own lens,
lente,
you
puede
can
jugar
play
con
with this
esta
table
tabla e
and
ir
set the
poniendo los
parameters
parámetros
that
que
you want,
desee,
seeing how
viendo
the
cómo se
fluoroscopic
altera
simulation is
la
altered.
simulación fluoroscópica. Es de gran
And it is
utilidad
very
y
useful and
reduce
reduces fitting time
el tiempo de
and the
adaptación
needs of
y la
changes,
necesidad de
as
hacer
important
cambios.
considerations in the case of
Como
topography.
consideraciones
The
importantes en el
important
caso
thing
de
is
las
to have a good
topografías,
topography.
lo
And
importante es
here
tener una buena
we are
topografía.
seeing the image of a
Acá estamos
topography
viendo en la
with
imagen
excess
una
tear,
topografía con exceso de
and the
lágrima.
eyelids are not
Los
completely
párpados no
open.
están completamente
A
abiertos.
lake is formed
Se hace
below,
un charco
which
abajo.
produces a
Ese
deformation
charco
of the
genera
reflex that
una
generates an
deformación del
alteration
reflejo
in the
que
topography.
produce una alteración en la topografía. Entonces es
And so
importante
it is
abrir bien los
important to
párpados,
open the eyelids
revisar
well
que no haya
and
exceso
check
de
that there is no
lágrima,
excess tears
evite el ojo muy
and
seco,
that the eye
porque
is
una
not
vez
very
está
dry,
seco
because if it
tenemos
is
buena,
dry
mala
we have a
imagen.
bad image.
En
And
los casos
in
donde
cases
haya
where there
glaucoma,
are glaucomas or
opacidades,
opacities,
podemos
we
poner
can
un poquito de
instill a drop
lágrima,
of
o
lubricant
si no
or
podemos
place a
colocar
very
un
thin
lente de
disposable
contacto
contact lens
desechable
of very
de
low
muy baja
gradation
graduación, bien
and on it
delgadito,
make a
y
topography.
sobre eso hacer
And
una
that is also
topografía
important to
que
look for the
también
tools
sirve.
that we have at our disposal
Es importante
to
buscar
obtain the
las
best
herramientas
possible
que tengamos
topography,
al alcance para
because
obtener
on
la
it
mejor
we are
topografía
going to take
posible,
the
porque
measures
sobre
and
eso
optimize the
es sobre lo
fitting.
cual vamos a poder trabajar en la adaptación. Bueno,
Well, if
ante
you have any
cualquier duda o
questions, I leave my
consulta,
email, and
dejen
I
un
hope you
mail
have found it of interest,
y
and
espero
see you
que
very,
les
very
haya
soon.
resultado de interés y espero verlos pronto.
And thank
Muchas
you very
gracias.
much.